The goal of today's lesson is to be able to tell the difference between representations of functions, so mostly linear, quadratic, exponential. And so we're going to look at tables, we're going to look at graphs, we're going to look at scenarios, and then we'll throw them all together and start comparing those functions to each other. So first thing, we're going to look at the table. So determine the function represented by each table and how you know. Well, the biggest thing that you can do is look at the rate of change for the table. So I can come to my first one, and I see that I'm adding by 3 every time. Because that rate of change is constant, meaning it's the same every time, it's going to be linear. I'm going to go through and also write the general equation of that. Y equals mx plus b. If you have something in that format, it is also linear. Okay, let's go to my next table. Let's see, minus 3, minus 1, plus 3, plus 5, plus 7. Okay, with this one, it's not a constant rate of change, so I know it's not linear. I can see it's following that 1, 3, 5 pattern. But sometimes, 1, 3, 5 only happens if your a value was 1 in the equation. And so I would suggest that you also look at the second rate of change just to see if that is constant. And there we go. Now I have, so the constant rate of change comes in the second rate of change. So this makes it a quadratic. And here you just need to have an x squared somewhere in your equation. There are lots of different forms. I'm not going to write them all. So just know if you have x squared, it's quadratic. And my next one, I see that it's multiplying by 3 every time, which means that this is going to be an exponential equation. Has what we call a multiplicative rate of change, meaning it multiplies every time. And our equation for that is y equals a times b to the x. Something to keep in mind there is that the variable is the exponent. Okay, that's how we can tell with tables. So I move on to graphs. We're just going to sketch each graph shape. Linear equations have a straight line. Quadratics are parabolas. Exponentials are pretty much flat and then they spike up. So it would be something like this. And then absolute value is going to be a V shape. Now we can go through just the scenarios, and we're just looking for things that reveal the rate of change. So, for example, the first one, every month the car insurance company deducts $5 from your payment for being a good driver. So, every month deducts $5. That's a constant rate of change. Which means that this is going to be linear. Okay, next one. Each point is exactly 1/3 of the previous point. When I'm not sure what that means, I know a lot of people say, oh, this is linear because it's 1/3. That's a constant rate. But let's look at some examples. Just pick any point. 27. What's 1/3 of that? That's 9. What's 1/3 of 9? 3. What's 1/3 of that? 1. And then I get down to 1/3. And I can see, oh, it's dividing by 3 every time or multiplying by 1/3 every time. So this 1/3 of, that of part means we are multiplying. So this is going to be exponential. Okay, the path the rocket takes when it is launched from the ground and where it will land. If it's launched from the ground and it lands, that's the path of projectiles. Oh, that's a parabola. So that'll be a quadratic. And my last one, the number of cell phone users is increasing by 75% each year. Well, that's a growth rate. And like we talked about with last lesson, if it has a growth rate or a decay rate, then it's going to be exponential. So now we're just going to compare functions to each other. All right, which function has a larger x-intercept? So I'm just going to look at these x-intercepts, and I see my quadratic. We're just going to take our best guess because those aren't exact. My x-intercepts looks like -2 and +10, because each of those are moving by 2. My linear looks like it's at 6, so that means that the quadratic has the larger x-intercept because it's where x equals 10. Which function increases at a faster rate? Exponential always increases at a faster rate than any other kind of equation. And something I want to make note of is the steeper the slope, the faster the rate of change. So for example, let's say I was just looking at the left side of this graph. My red equation here is exponential. I would not say that exponential increases the fastest if I'm just looking at the left side, because it's a pretty flat line. But as I go to the right side, because the exponential just shoots up and gets really steep, that's how we know it's increasing the fastest. All right, next example, we're going to look at tables and equations. Which function has a larger maximum? That is referring to our vertex. So I can look at this absolute value equation, and luckily it's in vertex form. Turns out absolute values only have vertex form, which is great. So that means our maximum value is 8. And then for this one, I can look at the table. I know it's formatted weird, but this is like the point 1, 11, 2, 7, 3, 11, so on and so forth. So I'm picking up the maximum. We're going to say the table because the table has a max value of 43. Okay, part B, which function has a smaller y-intercept? Something I want to point out with the y-intercept is the y-intercept always happens where x equals 0. So I can come to my table, and I have -4. For quadratics, this is in standard form, and so I could just remember that's the c value at the end, but also I could just plug in x equals 0. So, 6 times 0 squared plus 4 times 0 minus 3. 0 plus 0 minus 3. Point is we get -3. So my coordinate is 0, -3. So if it wants a smaller y-intercept, because this is negative, -4 is smaller than -3. Okay, once again, we could come to a higher maximum, and just as a reminder, maximum is referring to the vertex, more specifically the y of the vertex. And so then, as we, maybe a little bit, as we come to look at the equation, we have our absolute value function in vertex form of -2, -5. And for my standard form equation of a quadratic, turns out I'm not expecting you to remember how to find the vertex from every form, because guess what? We just finished a whole unit on graphing calculators, and so you can just type it into your graphing calculator. And when I do that, I think you get something like this. And we're going to change these instructions. So we're going to say max or min because the first one has a minimum value and the second one has a maximum value. And so we're going to say the quadratic, since it has a minimum is bigger than -5. Notice I didn't even find the specific coordinate of the vertex. I just can tell that it's already higher than -5. Okay, we're talking about a minimum this time, still at the vertex. This one's a little sneaky because we are transforming, like notice it gives us an equation and then a bunch of transformations, which means I have to transform this equation that it starts with. So first thing, with a vertical stretch by a factor of 2, which means I'm going to put a 2 out front. You know what? I don't even want to do this one. Let's just not worry about it because it's weird. Okay, example 4. You choose to invest money in a bank account that uses an exponential to calculate interest or one that gives you a $100 incentive to open and uses linear. Which account would you choose and why? I'm hoping you just had a Dora the Explorer moment and you just said exponential. Because it grows the interest the fastest. And our last example, a ball is shot from 2 different cannons. The first cannon can be modeled by the equation h of t equals -16t squared plus 40t minus 15. Nope, that's a plus 1.5. I was close. H is height in feet and t is time the ball is in the air. The second cannon shot can be modeled by the equation h of t equals -8 times x minus 4 times x minus 1. Which cannon shoots the ball the furthest? Okay, shoots the ball the furthest. Well, if we think about a graph, if I'm looking for something that's shooting a ball the furthest, that means I'm going to want to find something, mercy, okay. Shooting the ball the furthest is going to be this point, so we're going to be looking for the x-intercept. And I suggest using a graphing calculator because who wants to do that by hand? We're past that point. We are past that peasantry. And your window might be kind of weird. Just as an FYI, when you are typing this in the calculator, if you hit trace, well, first you type them both into y equals. So then when you go to graph, if you hit trace, the up arrow and the down arrow switches between equations. So then you could see which one is which. And so you don't even have to specifically find the x-intercept. So for example, when I graphed this, I got something like this for the first one. Honestly, didn't even see the vertex. I just made a guess based on what I saw on the graph. And then I saw this. And so, but it doesn't label it super clearly unless you put trace. So if I click trace, the equation will show up on the top left of your screen, and then you could see which equation is which. So even if my little blinker, my little cursor thing is like right here, it would show me, oh, that's my -16 x squared equation, and I see that that one doesn't go as far as the other equation. And so as far as an explanation goes, this graph counts as an explanation. Okay, if you have any questions, feel free to shoot me an email.